Let's build the following circuit. Take a source of DC voltage, a battery, and connect that in a loop along with a switch and two resistors connected to each other in series. So a circuit of this type is known as a voltage divider. According to Kirchhoff's rules, if we start at this point P and trace a path that goes around in a full loop back to point P, then the net change in electric potential has to equal 0. Or in other words, the net voltage gained around that loop has to equal the net voltage lost around that loop. So as we trace around, there's a voltage gain from the voltage of the battery. Here we'll use the symbol for EMF, treating this battery as ideal. And then there's a voltage drop, we'll call it V number 1, across resistor number 1. And there's a second voltage drop, V2, across resistor number 2. And so the total voltage gain is the EMF of the battery. The total voltage loss is V1 plus V2. Now, which of these two is the greater voltage drop depends on which of the two resistors has the greatest value. So what we'll do in this video lesson is derive an equation for the amount of voltage drop across either of the two resistors in this circuit known as the voltage divider. So here's the circuit drawn again. Let's start over with all the symbols. The EMF is the voltage of the battery. We've got a resistor number 1, a resistor number 2. So if we want to measure what the voltage drop is, we need to connect voltmeters in parallel with either device. So voltage across resistor number 1 is read by the first voltmeter, and the voltage across resistor number 2 from the second voltmeter. You can see I've also put an ammeter in the circuit. So let's start with this question. What would this ammeter read? Well, it's going to read the amount of current in this loop. By Ohm's law, I should be equal to the EMF of the battery divided by the equivalent resistance of the whole circuit. But since our two resistors are connected in series, it's very easy to calculate the equivalent resistance. It's just the sum of the two resistors, R1 plus R2. Now, that's applying Ohm's law to the total circuit, right? This is the total voltage around the whole circuit loop, and this is the total amount of resistance in that whole loop. But we can also apply Ohm's law in part. So if we apply Ohm's law just to resistor number 1, then it says the voltage measured across that resistor is equal to the current flowing through it multiplied by the resistance of that resistor. The current that flows through resistor number 1 is the current that flows through the battery, is the current that flows through resistor number 2. There's only one amount of current because everything's connected in series in this circuit. So by substitution, we can replace I with the EMF over the equivalent resistance, and so we get EMF divided by R1 plus R2 for the current, and we multiply that by R1. Or maybe we better state it as V1 is equal to R1 over R1 plus R2 times the EMF. And by similar logic, you should be able to convince yourself that V2 is equal to R2 over R1 plus R2 times the voltage of the battery. Of course, if we add these together, V1 plus V2, notice what we get. R1 over R1 plus R2 quantity times the battery voltage plus R2 over R1 plus R2 quantity times the battery voltage. So we can factor out the E over R1 plus R2, and we factored out, we're left with R1 plus R2, and then that cancels. But of course, this is just another statement of Kirchhoff's loop rule. The sum of the voltage drops across the resistors is equal to the voltage gain across the battery. Another thing to note is, what if R1 is equal to R2? Then how does the voltage divider work? Well, then the voltage across the first resistor would be equal to, let's see, if the two resistors have the same value, then we might as well just call it R without any subscript. So this would be R over R plus R times the EMF, which gives us R over 2R, which gives us half of the battery voltage, which means the voltage drop across the other resistor is also half of the battery voltage. Okay, so basically the voltage across any resistor is directly proportional to the amount of resistance. In other words, let's say we have, for example, a 12-volt battery, and it's connected to a 30 ohm resistor and a 10 ohm resistor. Okay, well, what's the voltage across the 30 ohm resistor? Whatever the voltage is, how about what's the voltage across the 10 ohm resistor also? So V1 and V2. Let's say the voltage across the 10 ohm resistor is X. And this means the voltage across the 30 ohm resistor has to be 3X. If it's 3 times as much resistance, then it has 3 times as much voltage across it. So the voltage drop in total is equal to 4X, but we also know the total voltage drop has to be equal to the EMF of the battery, or in other words, 12 volts. So the voltage drops have to be 12 over 4, which is 3 volts, and then 3 times that, give us 9 volts. Right, so 9 volts would be the voltage reading across the first resistor, 3 volts would be the voltage reading across the second, and notice if we add 9 plus 3, we get 12. Okay, so this is the nature of the voltage divider. Wherever you have the greater amount of resistance, you have proportionally that much greater voltage drop. The voltage across any resistor made of a circuit of 2 resistors connected in series, aka the voltage divider, is found by the equation R1 over R1 plus R2 quantity times the EMF. Likewise, the voltage across the other resistor is R2 over R1 plus R2 quantity times the EMF. There you go.